So in today's video, we're going to be talking about rotational inertia. We've already talked about torque and some rotational kinematics. So today we're just going to build on it with some rotational inertia and what that means. So as usual, I will have linked in the description the doc that is a review of all of this. And yeah, hopefully you guys enjoyed. This is part 3 out of 5 for the AP Physics 1 Unit 7 review. So hopefully you guys enjoy. All right, so let's start off with what is inertia, right? What is an object's inertia? So inertia is an object's tendency to resist acceleration, right? To resist movement. And so what we're going to call for the inertia for angular movement, angular rotation, whatever you want to call it, is we're going to call this moment of inertia. So this is going to be represented by I. So this is going to be an object's tendency to resist angular acceleration. So now we're looking at specifically angular acceleration. So with F of g, with an object's weight, we're going to look at mg, right? We're going to look at its ability to, or its tendency to resist gravity, right? Here, we're going to be looking at an object's ability to resist angular acceleration. So how do we figure this out, right? How do we figure out the moment of inertia for an object? Well, there's going to be an equation called cmr squared, where c is going to be a constant that is dependent on the body that is rotating, right? So if we look here, we can see these are some of the equations for moment of inertia. On the AP exam, they will be given to you, and if they are not, then we are to assume that it is just I equals mr squared, right? So if it just has a body with an inertia, it's just going to be mr squared. So what we need to understand is that for a object, the higher I is, so I going up, means that it is harder to rotate, and so it will rotate slower, okay? So it will move slower the higher the I is. So for a system with more than one object, how do we figure out its inertia? Well, we're just going to take the inertia of everything combined. So let's say we have, a person on a carousel. We're going to take the person and the carousel, add it up. That's going to be our inertia. We don't multiply it. We don't divide anything. We just add the inertia. So another thing we need to understand is that where inertia comes into play is we know that torque equals moment of inertia times angular acceleration. So we can use this to solve several different equations. So sometimes you'll be given torque and moment of inertia, and you'll be asked what is the angular acceleration, and you'll be given the torque and angular acceleration, and you'll be asked what's the moment of inertia. So we need to be able to use this equation to solve different questions. So let's take a look at this question. We're asked a solid sphere with I equals 2/5 mr squared that weighs 10 kilograms and has a radius of 1.2 meters, experiences a force of 5 newtons applied at an angle with 30 degrees with its axis of rotation. What is the angular acceleration of the sphere? Well, we should write that torque is going to equal IA. And so let's actually write this out, right? So this is going to be FR sine theta is going to equal 2/5 mr squared times A. So we can cancel out these r's and we can say F sine theta is going to equal 2/5 mr A. And so we want to find the angular acceleration. So let's divide everything that's not the angular acceleration. So first let's multiply the 5. So 5 sine F sine theta over 2 mr is going to equal A. So now we just have to plug everything in. So we'll have 5 times 5 sine 30 over 2 times m, which is 10, times 1.2, which is r. So we'll have 25 sine 30 over 20 times 1.2. So when we put that in our calculator, we're going to get that the angular acceleration is going to equal 0.521 radians per second squared. Okay, so let's look at this last question. So We're given that two blocks are joined by a light string that passes over the pulley shown above with a radius of r and a moment of inertia I about its center. We're told that T1 and T2 are the tensions in the string on either side of the pulley, and alpha is the angular acceleration of the pulley. And then we're asked which equation describes the pulley's rotational motion during the time that the blocks accelerate. So we should remember that the torque is going to equal I times alpha. So let's write this out. So FR, and our sine theta is just going to be sine 90. So it's going to be 1. So we don't have to include that. So FR is going to equal I alpha. So what is our force? Well, if we look here, we're going to have a tension going this way. And I should actually say it's a tension going this way. And we're going to have a tension going this way. So our total force is going to be T2 minus T1. And then we're just going to have times R equals I alpha. So we look for one of those answers, and our answer is going to be C.